Yeah, welcome everybody to the next webinar of Würth Elektronik ISOs. Our topic today is Discover Radio Communication. We've got the recipe for the most simple wireless connectivity. Today's speaker is my colleague Manfred Schommerz. He's internal support engineer of the division Wireless Connectivity and Sensors. And my name is Regina Fingerhut. I am marketing manager also for the division Wireless Connectivity and Sensors. I will now give you some general information about our webinar today. The duration of the presentation will take around 30 minutes. After that, you have time, we scheduled 50 minutes for that, to ask us some questions. But if it's not possible for us to answer every question you might have, you can also write us an email under isos-webinar@we-online.de. It would be great if you can answer a feedback questionnaire after the webinar, so we are able to optimize our webinars for the future. The recording of the webinar will be available one day after the presentation on our YouTube channel Würth Elektronik Group and also on our homepage we-online.com/webinars. Just another information, you are muted during the whole webinar, but it's possible for you to ask us the question via chat function. Now I will give the word to my colleague Manfred Schommerz.
Yes, good afternoon, ladies and gentlemen, webinar participants and everybody else, and also a special thank you to Regina for doing the introduction. Yes, I've been asked to conduct and carry out this webinar this afternoon with the topic of radio communication and how simple it is to build up a simple link or connection. Let's get straight on with it and see what do we have available. These are some of the topics I'd like to discuss today, starting off with the introduction and then some basics because RF is very complex. We'll go through some basics and talk about frequency and technology. We'll talk a little bit about the design in of a module to get a system running, concerning the hardware, software, and also a bit of certification themes. Right, there is one slide on network topology, which is always very interesting. And then from there, we'll go over to our evaluation boards, the Amber Pi, a little bit about our added value, and a short summary. On the right-hand side, you can see a picture of two of our modules. What is it all about? What do we want to achieve? In the olden days, we had a cable, and it was very simple. You'd apply a voltage or a current, and you could transfer a signal. Very often, however, this is not possible, and you would like to transmit via radio signal some other data or information. And what we have here on the left and top is a little graphical representation. We'd like to enter some other digital data via UART to a module, which would be this part there, which takes part or takes care of all of the radio communication, transmitting via electromagnetic signal some data, and on the opposite side you would have the equivalent to do the reception. Right, that is in essence what it's about. Let's have a look in a little bit more detail. To get this data across the air, we need an electromagnetic wave or signal, and that is a little bit more complex than a piece of wire. What I have here is on the left-hand side the transmitter, the TX radio with an antenna, then the red section, the transmission path, and the right-hand side, the receiver, doing the opposite side. Now, throughout the whole sequence, there are obviously power losses, and in green here I've tried to indicate that even in the coax and the antenna we have some power loss, but what you see in the red curved line here, this section indicates to me that I have a signal loss as the signal is radiated, And the reason why it's curved is we are talking in decibel, and decibel is a nonlinear function. And then on the receiving end, on the right-hand side, the RX power is a little bit of radio signal we receive. We have some losses there as well. And what is left over on this part, the margin before, or the minimum level where we can still recognize any sensible data coming in. The difference between these two is our link budget. The budget we have available of radio signal to work with and to get our data transmitted. And there are a few interesting and very important factors here. You'll see that obviously I have distance. I have indicated here and shown you a graphic representation of the transmitter and a receiver certain height above ground. And for any radio transmission, obviously we need a clear path, a clear view with little disturbance or material in the vicinity to absorb the signal. So the height above ground for an antenna is very important. The antenna itself is important, and then obviously the amount of power we have available. Let's carry on to the next slide. Before we need to have a little look at a bit of theory and mathematics. I've mentioned in the previous slide, we work with a so-called link budget. That is the power we have available to get across in the electromagnetic field. Here you'll see that at the top, the link budget in decibel consists roughly, I've abbreviated this, from the transmitted power minus the sensing power, the sensor receiver power. The model we've seen on the previous page as well is a two-way ground reflection model, and this is fairly reliable, to give us a distance with which we can start calculating and working with. I'm not going to go into detail of this simplified mathematical formula, but have a look at the graph on the right-hand side. For the different heights of antenna, there is a significant increase in signal based on the link budget at the bottom. So if you have a fair amount of link budget available and a good height of antenna, in our 2.4 gig module, we have closely on 5 kilometers already with a clear line of sight, and we could get as far as, in this case, close to 10 kilometers with our 868 module, the latest one available. Right, there's a little bit of information, the points we need to take care of when we want to transmit a signal. I've mentioned that one of the elements is the antenna. Now, the antenna serves to convert our electrical signal to an electromagnetic signal to be sent over the air. Apart from that, you'll see that we need to modulate our signal, our data, onto some other carrier frequency. And this carrier frequency, invariably for the short-range devices, is 868, but also 2.4 gigahertz or 433 or 169. The binary input data gets modulated on top of the carrier. There are various methods of modulation. This is the so-called frequency shift keying modulation, FSK, or the two-position FSK. There are other forms of modulation, which could be the QSK or even OOK and various others, plus the 4 minus FSK. The radio guys will know what this is about. Find the most optimum form of modulation. And once we have the signal modulated, we have an RF signal containing our data. And this needs to be transmitted via an antenna. And on the right-hand graph, you will see the spectrum which we get on the radio signal. The right-hand top, there's a little screenshot of our signal analyzer, and you'll see the two little peaks adjacent to the center frequency. Now, the center frequency is normally your carrier frequency, which would be this guy here. In this case, I think if you look at the right-hand picture, it was 868 with something and a little offset to the left and the right, roughly 50 kilohertz, containing the zeros and ones, my digital data. You'll see that there are a dotted line and a fixed red line. I've showed them as purpose. Normally the module as we provide it would have a signal spectrum similar to the dotted line, but once you've designed this into your final product, it could still be affected by the housing, by the environment and various other factors. And eventually you get the end device spectrum, the red line, which I've shown in the red on this graph here, which would then be the final product. Now, this is the reason why we recommend, apart from our certification and test results, the final product put on market needs to go for a final end test just to make sure that you are well within your limits and calculations. Right, this is a lot of theory. There's one bit more of theory which I'd like to have a look at. To get this energy across into the air, into an electromagnetic form, normally we talk of a dipole, a positive and a negative of an antenna, or for that matter, a monopole. What we have on this graph here is in fact a representation of a piece of wire or antenna, an electric conducting material, and the other part of this half wave would then be folded or integrated into the ground plane. This would be the simplest implementation on a PC board. Alternatively, you would have a monopole antenna. And I'd like to show on the middle graph here the maximum power delivered at a quarter wavelength is when an antenna is at resonant frequency. Now for 868, this is about 32 centimeters for the full wavelength, and a quarter wavelength is something like 8.3 centimeters. Now the antenna leg, the one part which would be the transmitting, would have about 8.3 centimeters of length. If resonating, we would like the voltage at the ends of the antenna to be maximum, and the current at the middle, at the feed point, would be the maximum, and this would then oscillate up and down at your 868 megahertz frequency. Right, standing wave ratio is the term here. This modulated signal needs to have little reflection in order to get the maximum of power output, and eventually out of that we'll get a emission pattern as can be seen on the right hand side here, which would then represent a vertically standing monopole antenna to get the maximum of range. Right, without further ado, let's have a look. I've spoken about antennas. There are various types available. The classical, originally known, was a wire or the dipole antenna, but we also have PCB or chip antennas. Now there's a picture of a chip antenna or a design of a folded PCB antenna. The reason for this is simply a fact or a matter of cost and size and space. Very often you don't have the external size and you are not reliant on extreme distance, so then you could go for a chip or a PCB antenna, the PCB antenna being very cost advantageous. Alternatively, you'd have to go to a dipole, external dipole antenna of various types. There are many options. Have a look at the antenna options which are available. Now, once you design this into your PC board, I've shown this on one of our USB RF adapters. The signal from our module as it goes out of the RF pad, and you'll see the gray path here, needs to be designed to have an optimum of 50 ohm impedance in order to have a minimum of loss and a maximum of power transmission to my antenna, which then is transmitted via, in this case, a SMA, or you could connect it straight to a wire or to whatever antenna you have. The reason I'm mentioning this is that during design-in, take care about this antenna line or path on your PCB, and the best would be to make provision for some filtering and ESD protection equipment. The top here would be a coil for ESD protection, And this here, if you turn it on the side, looks like a pi signal, therefore typically a pi filter, which gets rid of harmonics and spurious emissions. And because you can never design an antenna path 100%, make provision for this so that after production of the PCB, you could still do minor tweaks or corrections on this to get the maximum power output. Therefore, I've shown here a little bit of a cross-section, what needs to be considered if you design this PCB board of yours with a specific antenna path, and there is a lot of documentation on it. Relevant and important here are the length of this path, keep it as short as possible, the width and the thickness, and then the height above the ground level. And there are two more elements here. The one here is the epsilon, the material parameters. In other words, what material is my PCB made out of? Is it some resin or glass? The parameter could be somewhere between 3 to 6.1, which needs to be considered in the calculation. And then we have a little factor, the tangent D or tan delta, which is the loss factor in the actual path, the magnetic loss tangent. And if all of that is good, you have a good matching network. In other words, the maximum power going to the antenna at resonant frequency. Right, let that be enough of the theory. The design in, here I have a little picture of one of our modules and what you need to do in order to design it into your system, your host controller. There are just a few lines in the minimum function which you need to connect. Obviously, the power and the ground, which in this case would be the two lines here and here. But most important is the TX and the RX, the transmit and receive. And those are the two lines, the UART lines, which you'd connect to your FTDI or to your host controller. And one or two other control lines like the boot line and the reset line. And with that, you could in fact already be up and running, connected to your host controller. Be careful, you might still need some software on your host controller to actually communicate via UART. Let's have a look at some of the network topologies, just briefly. In essence, the radio communication would work from point to point or in a star topology. Because radio transmits in all directions, many other partners could actually receive and listen to the same signal. That needs to be taken care of. If in this case, as in a peer-to-peer connection, you need to make use of some form of addressing. So in your data package, you would have to put in the address and the destination. And it could be as complex as using a mesh system, whereby if you'd like to achieve greater ranges, you could actually make use of a so-called repeating function. And there are many variations to the topic, but be careful, repeating is complex and it is at the cost of energy, your energy budget. If you are battery operated, you need a good and well designed system, but obviously very interesting to increase your range. A little bit to topologies. I'd like to skip to the next foil here, the next slide. I've mentioned SRD previously, the so-called short-range device frequency bands, which are license-free, but they are with regulations, so there are rules and regulations which you need to adhere to. Have a look at the European norm EN 300220, which concerns the 1 or sub 1 gigahertz modules, and also the EN 300-440. These specify the technical characteristics and methods of measurement, and also other essential requirements according to Article 3.2 of the directive of the RED. A little bit of theory. Take note, under frequency, there's a 169, the 433, and then the 868 bands, as well as 2.4. Just to mention, there are 4 basic bands with sub-bands underneath them. Most of them are limited to 10 dBm. There are 1 or 2 exceptions, 27 dBm, or 500 milliwatt. The power output, be careful in designing, there is the term duty cycle. Now these are determined by legislation, and in essence, if you have 1% duty cycle, this is 1% of the total time per hour which you are allowed to be on TX, on transmit. One of the limiting factors, have a look at that, but you have the option of PSA, a so-called polite spectrum access. In other words, you look at the channel before you actually transmit to see if it's clear. I've mentioned the duty cycle and the channel spacing and some notes. I'd just like to point it out to you, take care of this and plan this well in advance before you actually go and design a RF system. Now, because it's so complex, the easiest is simply to use one of our modules, which is pre-measured and calculated according to all the EN norms and rules. For that, take care of your target market. Is your market European, American, the Far East? Because there are different legislations valid. They even have different frequencies which are relevant. For example, in the USA, the 915 opposed to the 868 in Europe, and also the RF technology you'd like to use. Right, proceed with your design in. 2 points of importance here is the actual interfacing via UART, the layout of the whole system, and the antenna. Interfacing and antenna, very important. And once you've finalized your product, we suggest for a final test to check and see if it's within limits and to get rid of possible spurious emissions and so on. Once again, contact your accredited laboratory. You can always use our initial test results to support your final test, and this would allow a much simpler final test on your side. In order to be able to do a self-declaration or a declaration to be able to place this product on the market, which be the CE sign to be placed on any product in Europe, or FCC for America, or whatever else in the country it would be. Right, take care of these points. I hope I'm not going to dwell on this. There's one more topic which I'd like to go. This is a little bit more theoretical. What else is actually involved on our module? Once you've designed it in, you'd actually like to take it into operation. Now, on our module, there is a software stack programmed and flashed on there, which has an option of either operating in the so-called command mode or the transparent mode. The command mode simply offers you a lot of commands and options to communicate with the HF module, which then takes care of the radio transmission. And in fact, once you start it up, there's a bit of delay, which I've shown here, until the release pin is available. So you'd start the system, make sure the voltage is stable, and then release, and thereafter you'd get a feedback from your module, which would then say, right, I am ready. That's a command reset indicate, the reply which comes back from via UART from the module, and thereafter you could further communicate with the module whatever command you wish. Either give it your package to be transmitted and so on. The 8826 works at 15,200 baud. Most other modules at 9.6K baud. This is a picture of a typical command. In this case, the command reset indicate is the command that would come back as soon as your module is available for operation. The values in hex here, starting off with 02, the actual command, the length, the mode of operation, and a checksum. Let's have a look. Once you've started, obviously I want to get some data across, and remember a little pictogram right at the beginning. The digital data which I'd like to get in here and actually have received on the opposite end. This is an example of what would happen in terms of software on the module. It would get a transmitter signal with the following package: the start signal, command length, and the payload. Yes, this payload is old and well known. It says hello world, all in hex, with a checksum. The receiver, however, wants to receive this very signal, and for that matter, do the unpackaging and transmit or pass on via UART the very same information. Now let's carry on right from there. There are many more commands available in the software stack. And one of the elements which are put in here is the shutdown. Because RF and battery operation is dependent on an optimized battery consumption, we would like to shut down the module while it's not transmitting or not necessary. So we'd have the option of actually shutting it down. There are various levels, either in a sleep mode or a power down mode. And you would send it a command, and the command would be shut down, confirm. That would be the answer coming back. So this would be on the UART side and not on the RF side. Right, now our module would be in this case in a shutdown mode. The only way to get it back up and running, because now the UART is also sleeping, would be to use a wake up pin or something similar from your host controller. Have a look. I've put in here the typical currents for receiving is 8 milliamps. I think the TX is around about 20-23 milliamps, depending obviously on your power level. But the shutdown is the important part here, down to 0.2 microamp. And that is all the spaces in between whereby we can really make the battery operation very, very long. Months up to years of battery operation. And that is what we need for IoT applications. Right, a lot of theory there. How do we assist and support you? We actually have evaluation kits for all of our modules. And here are some pictures. The advantages are that for or with our modules, the evaluation kits, we give you a ready-to-work solution, which already has included the FTDI driver in this case. The antenna connection would be available, a pin header or more to do or connect external test equipment, and also the option to do current measurement on your board. Right, if you use a board like this, you'd connect it via USB from one side. There's a FTDI driver here and our module with the antenna on that side. The bigger module with the antenna there. You could, on the other end, simply use one of our stacks or a second board to complete your bridge of communication. Right, this is a lot of information and theory. Let's carry on one or two more slides here. We have a very interesting product, the Amber Pi, which allows you to experiment with RF as well in a very quick, easy, and simple fashion. Graphically, or the picture on the right-hand side is the Amber Pi with, at the bottom, a number of sensors available, from pressure, temperature, and the 3-axis gyro. The 3-axis gyro being this here, and a bit of a space for your own development. All of that, including our RF module, plugged onto a Raspberry Pi if you wish. And this is a nicety. All Raspberry Pi fans will know that either with Raspbian, a Linux-based system, you can very quickly and easily play around, write your own application, and read the sensors and transmit the data. We have a number of options available here for most of our modules as well. We also have the drivers free to download from our homepage. The system could even be used standalone without the Raspberry Pi, which would then entail the board as can be seen here. However, you'd have to have a bit of own software running on our AMB8826, which has some spare memory available, and the module would then read the sensors and do the communication via RF. A nice, interesting little experimenting device. Remember our Quickstart earlier on. Now, in order to do the transmit and receive function, which you see here, we've actually included in the AmberPi a so-called SDK, a software development kit. And this provides you with all the source code in C for, well, most of our SRD modules, as well as our USB sticks and even our wireless M-Bus modules. It has implemented command interface for most of these modules. And looking at this picture, you'll see, remember previously, we had to take care of the data request and the communication to our module, in other words, via UART. But now, with the SDK and AmberPi, you could simply do this from or within your application. It would send the same package for you, and the SDK with the drivers, the functions available, would do the rest of the work for you. So very easy. You write your application with your whatever you'd like to put in there. We take care of everything else. The receiving end, the same process in reverse direction. The module would indicate to me that there's data available. The software development kit would check this data, extract whatever is in it, and my application ends up with the hello world or my sensor data, which has been received. This is available for the 8826, most of our modules, for our wireless M-Bus, as well as for the sticks. A little picture here to maybe summarize it a little bit more. Yeah, we tested with the Raspberry Pi 3 Model B with the Raspbian, but other options, other models are also available and should also work quite well. It provides you with a simple execution, editing, debugging, and so on environment, and all Linux and Raspberry Pi users will know how to appreciate this possibility. Right, if you have a look here, the Raspberry Pi could read and could also allow you for connection via Bluetooth or Wi-Fi to some of your peripheral equipment. It also allows you the keyboard and monitor. But you could directly go via our RF module to whatever end product you'd like to use. So the possibilities are great. Yeah, folks, we spent a little bit of time over the last few months to give you some interesting video to play around with and have a look. I wish you good luck and fun having a look at these. It's simply unboxing the AmberPi, but more important, taking into operation the AmberPi. So step by step, 10 rules of how to get the whole system into operation. Have a look at this. I'm not going to dwell there. One more slide, and I'd like to summarize what do we have available to get this wireless bridge going. I'm not going to go in detail because the print is fairly small, but what I'd like to point out is that we have low power modules in the sub 1 gigahertz range. We have a high performance module, and we have modules on 2.4 gigahertz. We even have a Bluetooth module on 2.4 in a very small and tiny format. Apart from that, the wireless M-Bus products, very often on the same hardware platform. And as a nicety, we have the supporting radio USB adapters on the same frequencies. You could, in essence, use the stick as is, or use a module, or use a mix of the two. The same goes for the wireless M-Bus, also available stick, and the AmberPi kit here. I'm not going to dwell on this for much longer. These are all our products on 169, 343, 868, and 915, and 2.4. This seems to be just about the last slide. I have to keep an eye on my clock here. We'd like to just quickly summarize. We can also support you with customized software solutions if you have a special design or equipment or wish. We can help you with special features, in other words, design in and so on. Also with the antenna design, But for the antenna design, also have a look at the reference designs, which are very often available and are a good reference to look at. We supply you with the pre-measured and pre-certified radio modules. And with the pre-certified radio modules, there is not much more you need to do. Finally, you've constructed your own radio communication, other than maybe doing a final test and adding the CE conform label on there, the CE label, and you'd be off onto the market. Without ado, I think, or I hope to have summarized a little bit what is available and how easy it is to set up a radio link. I thank you very much for your attention. Please stay on and use our chat function to ask your questions. I am just going to glance across to the opposite side of one of many of our windows which I have here to control the whole web session and the webinar and the control room at the back. Right. So at this stage, I will stand by. I'll hold this section here. You are welcome to carry on and ask. I'd like to thank you and the whole team behind me for the support. We'll stay online and yes, looking at the questions. There are one or two questions coming in here. Yes, let me quickly see. Where can I find further documentation? One of the customers here writes, where can I find documentation? Yeah, documentation. We have documentation available on our homepage, which can be downloaded if you scroll down to the bottom under downloads of most, or in fact, all our modules. Also have a look at we-online.com/wireless-connectivity. So a lot of documentation available, and for the Amber Pi, even a lot of source code in C also available. Yes, I'm keeping a further eye on the questions. One of the questions here, could you help me to find the right frequency for the country I am in? I might just add that there is no rule for the whole world. 2.4 is possibly the most widely spread. 868 is also very common, but yeah, certainly we can like to help you. Give us a call or send us a mail, use our service functionality, and we can do a bit of research and see what modules we have available with a lot of certifications and allowances for the Americas, for Europe, for some of the Eastern countries, and we certainly like to help you with that. It's my pleasure. Keep in touch. Not everybody will see all the questions coming in here. There is one question here. Do you support me with antenna design in my product? Yes, certainly. You're welcome to ask. We will be more than willing to give you support and antenna design in. Also have a look at the lot of reference designs, which are always well specified, or use an external antenna like our AMB 1981, which is our little stub antenna. It's delivered us with very good products. Or alternatively, within Germany, you could simply contact one of our FSEs, field sales engineers. They'd always be keen to help you. Yes, I have to just check and see what else is going on in the question form on the left-hand side here. If you are still online, you're welcome. Ask your questions. Our team in the background will try and answer them one by one. Yes, oh yeah, okay. Okay, one more here from a certain client. I would like to start a design. How long does it take to receive samples? In fact, we have most of our modules on stock, ready and available. Depends on the quantity, but usually either a development kit or a so-called development set, or smaller quantities of modules are available at a very short range or off the shelf. Contact us and we'll see what your requirements are. Obviously, bigger volumes then take a little bit longer, depending on the quantities. I hope that answers it more or less, but for initial testing, we always have samples available off the shelf. Yes, the other question here relates, or very similar. Where could I get hold of samples? Yes, just contact us, either from us directly or from one of our field sales engineers, or you could even go through one of our distributors. I have a question here which has come up, a more technical question. In terms of range, what is the reliability of range? The range which we indicate normally is a free line of sight range, and we have tested all of those, but range obviously is dependent on many factors. Obviously, PCB antennas or chip antennas won't have that range, but you don't always require it. It would be a compromise between cost and space available and various other factors. But with a good XL antenna and suitable height, the ranges stated are also very realistic. We recommend that before you implement, do a test on site and see what and how you could get through the best. Production. Yes, a little bit of silence here. I need to monitor the different chat and question windows I have open here and not try to lose control. In the meantime, I'm just going to freeze my screen at this stage because I have a few monitors open here which I'd like to jump across and go through. Let me see, there are one or two questions here which aren't maybe all that interesting. Here's one more question. What is the effort to switch from 868 to 169? Goodness, yes, well, the effort switching, you'd have to do a bit of redesign. In other words, the modules, if you use a module, would be a total different one. From your controller, obviously you'd have to design in a new module. From 868 to 169, obviously it's a new frequency, a new wavelength, a new antenna. So it's not as easy as just plugging in a new module. There's a lot of peripherals that need to be taken care of as well, especially the antenna. Be careful. For 169 also different and lower data rates might be applicable or might have an effect. So your interfacing via UART, take care of that as well. Right, gentlemen, ladies, at this stage, I'm looking at my clock on the wall here. I have had great fun. I've enjoyed this. Thanks for the questions and the support, and we hope to hear and see you again at the later stage. I'm going to end the session then. Good luck and bye-bye.